va donc passer à la séquence séminaire de cette session. Et c'est un très grand plaisir aujourd'hui d'accueillir Jean-Philippe Brantut dans le contexte de cette série de cours et séminaires. Jean-Philippe a été pendant très longtemps dans le groupe de Tillman-Esslinger à l'EPFL, dans lesquels il a réalisé de magnifiques expériences de transport, des expériences véritablement pionnières où il a pu observer différents phénomènes comme la quantification de la, entre guillemets, conductance entre deux réservoirs, parmi beaucoup d'autres résultats. J'ai eu le plaisir de collaborer avec lui sur certains effets de transport couplé d'entropie et de transport de particules à cette époque. Et puis, depuis cette époque, Jean-Philippe s'est installé, a été recruté à l'École polytechnique fédérale de Lausanne, où il a monté deux belles expériences d'atomes frais en cavité. Il va particulièrement nous parler de l'une d'entre elles aujourd'hui, celle où il cherche à réaliser, à contrôler des interactions à longue portée, et peut-être réaliser le modèle de Sajdiefie-Kitaïev. Pour monter ses expériences, il a obtenu 2 ERC successivement. Et c'est un grand plaisir d'avoir Jean-Philippe aujourd'hui pour donner séminaire. Je lui laisse la parole.
Merci. I've prepared everything in English. I don't know.
That's fine.
Okay. C'est un peu. Oui. Okay. So I don't know. I thought the tradition was to give the seminar in English, but feel free to ask any question in French. So thanks a lot for the kind introduction. It's really a great pleasure and a great honor for me to be here. I'm going to tell you about the experiments in which we are using ultracold fermions, ultracold fermionic atoms, and we are studying them as they interact with each other, and they are interacting in our situation simultaneously at short distance through the mechanism that Antoine has been describing in the first lecture of this, first part of the lecture of this morning. But they are also interacting with each other at long distances, and they do so by exchanging photons with each other. And the main player of this presentation is going to be high-finesse optical cavity, which is formed by 2 mirrors of high reflectivity facing each other and allowing for strong light-matter interaction in addition to atom-atom interaction. So that's the main topic that I'm going to cover. Before I come to that, this is probably the most important slide, and I'd like to give credit to the people who have been working on this topic. So I will say things like, we do this or we do that, and it's understood that when I say this, these are the people who are actually doing it. And I'm mostly reporting their results, so all the credits should go to them. I also would like to thank a number of theory collaborations that we've been developing over the last few years. As the systems we are studying become more and more complicated, it's very important, even at the level of qualitative interpretations, to have inputs. And I will mention their contributions when they become relevant, but this is something without which we would be most of the time clueless. Okay, so let me start with a relatively general introduction, even though you heard quite a bit already if you followed the lectures so far about the general framework in which our experiments are operating. So we are trying to create synthetic quantum systems, and we are trying to do it by adding layers of complexity one after the other, starting from clean systems like atoms, isolated in ultra-high vacuum, and then building a many-body system sort of from bottom up. And in doing so, the hope is that we can have new emergent phenomena that show up, which can be surprising, that can have some correspondence and differences with respect to condensed matter physics that could be interesting. And one of the most interesting aspects of these, the quantum gases we are studying that's sometimes overlooked is the fact that they are extremely dilute. And we have a situation in which the interparticle spacing is about the wavelengths of visible light. And that's why we can use lasers, we can use microscopes, we can use optical methods in general to control and manipulate the atoms at the smallest relevant microscopic length scale. And that's really the tool which makes it possible for us to use light-matter interaction to shape these systems. I would like to emphasize on 2 points which are somehow differ. Let's say they are different between electrons in solids and let's say atoms differ from electrons from 2 points of view. One of them is the fact that they have an internal structure. And that's something which is very useful. Atoms are neutral, but the way they interact with each other is controlled by the two-atom problem, so basically by physical chemistry process. And that's something which we can leverage in order to change the way atoms interact, and that Antoine has touched upon this at the very beginning, and that's going to be something which we use in this presentation. This internal structure also has one important consequence, is of course that there is direct dipole coupling with light. So atoms have many levels. They are coupled by dipole-load transitions, which means we can send photons onto atoms and have the possibility for the photon to actually be absorbed, re-emitted, and scattered in ways that elementary particles usually don't do, or they don't do to the same degree. And that's of course something which will play a very important role in what I'm going to tell you about. And the kind of quantum system we are interested in will be one where we have at the same time strong atom-atom interaction and strong light-matter interaction. And it turns out we can actually enhance these two to the point that new phenomena emerge because these interactions start to dominate the other energy scales. And I'm going to tell you what happens, what we have learned about this, and what we actually can do with that. We think we can do with that. So very, very short about enhancing atom-atom interaction. And again, I don't want to repeat what Antoine has been saying this morning. But essentially, two neutral atoms interact by van der Waals forces. They are polarizable but charge-neutral objects. So the interaction potential is very short range. It's much smaller than the interparticle spacing. And because of the internal structure of atoms, typically at large distance in a magnetic field, collisions happen in the triplet channel. But there can be a small, say, hyperfine coupling, dipolar coupling, with other spin configurations when the two atoms come close to each other. And when that takes place, you can have a resonance if there is a bound state, for example, in the singlet potential that becomes close to the scattering, to the energy of the incoming particles in the triplet channel. And that gives rise to a resonance phenomenon, which in our jargon we call Feshbach resonances. And that's here the special case of lithium-6, which is the atom that we are studying in my lab. It turns out that at 832 Gauss, you have one of these resonances at which the scattering length is diverging, so the atom-atom collision is basically resonant. By operating the experiment at the homogeneous magnetic field in this region, we are actually creating a very strongly coupled system. This is the unitary Fermi gas. It's a relatively well understood system. As you cool down a gas without lattice, you just start at high temperature, perform evaporative cooling all the way down to temperatures of the order of 10% of the Fermi temperature. The strong coupling here gives rise to pairing, Cooper pairing, and what you obtain is a nice S-wave superfluid. If you're used to superconductivity, it's the same physics, except the coupling is very strong. The binding energy is of the order of the Fermi energy, but from the point of view of symmetries, it's a well-behaved S-wave superconductor or superfluid. And that's, think about it in the framework of this talk as a bulk material. That's what we start with, and then we add on top of it the light-matter interaction. So how do we enhance light-matter interaction? We just put the atoms in between two mirrors. So why do we do that? Well, if you think about an atom here, that's prepared in an excited state. It can decay by emitting a photon. And in this configuration, two things can happen. Either the photon is scattered away and lives in free space and is lost kind of forever, or it is emitted in the particular mode that is sustained by the high-finesse cavity. The ratio of probabilities between photons being emitted in free space and photons being captured inside the cavity is a dimensionless number. That's called the cooperativity of the cavity. It turns out that that cooperativity is proportional to the finesse of the cavity, which means basically how good the mirrors are. If you have very high reflectivities, you can have finesse of the order of 10 to the 4 or 10 to the 5. And that cooperativity can then be made very large. And if it's larger than 1, typically the light-matter interaction is dominated by one mode of the electromagnetic field and the atoms as opposed to the rest. And you single out this mode, and there the interactions between the photons and the atoms are coherent. And that's the regime which we want to reach. And for practical purposes, at least for the purpose of my presentation, the cooperativity is the only thing you need to know about cavity QED, right? That's why we actually do high-finesse cavities. That phenomenon is actually classical. It's very nicely explained in this paper here by the Vuletic group. It's a classical interference effect which sort of forces the atom to emit in this particular mode if the finesse becomes sufficiently high. Of course, that's not everything that there is about cavity QED, and of course, this is not any place in this respect. There is, of course, a huge legacy of experiments that go way beyond the regime that I'm going to explore. You can use this cavity QED to realize quantum information protocol to explore light-matter interactions in ways that go way beyond anything that I'm going to say. So we are standing on the shoulders of giants. I just want to mention that the little bit we need to know is this one, but there is, of course, way more about this. Of course, Serge Haroche has been doing this in particular. But it's still growing, but in directions which are a little bit different than the scope of my presentation. So that being said, this is how it looks like in practice. So that's a picture of about half the optics we have in the lab. And if you were to look here under this whole bunch of optics, you would find a vacuum chamber, and inside the chamber we have our high-finesse cavity. So these are the two mirrors facing each other. That's a macroscopic object, so 4 centimeters between two mirrors. This is handmade, like assembled literally by hand by my first PhD student. And inside the cavity here, we are making all the cold atoms business. So we laser cool the atoms, we trap them, we evaporatively cool, and so on and so forth. And after 2.5 years of very hard work by my students, you actually get inside here, in between the two mirrors, a unitary Fermi gas at temperatures of about 10% of the Fermi temperature, which is low enough for the system to be a well-behaved superfluid. That's an image of Bose-Einstein condensation of molecules, which we can obtain in a regime where the binding energy of fermions is large enough. So that's something we've produced, and we've invested quite some effort in optimizing and developing the experiment itself. So if you're interested in the technical aspects, there are a few innovations that you would find in these papers. So, okay, this is the starting point. I'm going to tell you a little bit about cavity-induced interaction and how the light-matter coupling gives rise to long-range interactions. And then I'm going to explain the main phenomenology which comes out of it, which is the formation of charge density waves. And there I will give a sort of overview of what we've been doing in this respect without entering into too much details. But the goal here is to give you a flavor of what's going on in there. And this is something which we are still studying with refined methods like microscopy in particular. And then I'm going to spend a bit of time describing 2 examples in which we go beyond this phenomenology. The first one is another way to use the cavity in order to produce what we think is actually a pair density wave state. And that's a something where I'm actually interested in having some feedback from a condensed matter physicist. This is something which is a little bit exotic for us. So I will show you where we are and what we think we've been doing in this respect. And then I will show you how one can, based on this mechanism of cavity-induced interaction, tune the system, trying to go towards the realization of the Sage-Defty-Ekitaev model. We are not there yet. But this is a topic which we've been studying with the help of a team of theoreticians over the last couple of years. And now it seems like it's probably possible to reach a regime in which the SYK physics should show up in some limited range. And I will show you what we think can be done, also where the challenges are, and how we are attacking this problem, and maybe some things which we could try to investigate on the way there. So that's the plan, and in any case, if you have any question in between, feel free to interrupt me. I probably have a little bit too much material. I'd rather stop before the end and give a bit of time for discussions. So let's start with cavity-mediated interaction. So we have this one mode of the electromagnetic field that's at frequency delta C here. A and A daggers are creation annihilation operators for the photons in this particular mode. And the light-matter interaction is described by this coupling here between density and the intensity of the total electric field intensity. And this term here is the important one for this presentation. And there are two complementary ways to interpret it. One of them is to say, well, these are atoms, the total density of atoms, that feel the dipole force exerted by the light intensity that's in my system. Phi is the electric field. So that's the point of view of the atom, so they just see the force exerted by the photons. But there is a complementary version, of course, which is to take the point of view of the photons, and from that point of view, this is just the refractive index of the atoms that we've been putting inside the cavity. We are operating in a regime where the photons are never actually absorbed, right? So we work far from the atomic resonance, so that there's basically only refraction. And these two are the same thing, right? So there's just two different points of view you can add up by looking at this term here, and the two of them are useful. Now, the total electric field here comprises one contribution from the photons inside the cavity, that's this one here, and there can also be an external classical beam which we also send onto the atoms that acts as a pump in such a way that when you expand the phi dagger phi here, you're going to get interference terms, and these are the things which we are interested in. But practically, the light-matter interaction, you can take these functions here. These are mode functions, like a cosine for the Fabry-Perot cavity I have here, a plane wave or a standing wave for the transverse mode. And you form some collective atomic variable theta, which describes the parts of the atom that's coupled with light. So there's this here, and that's typically a density wave, right? So it's a density times interferences between standing waves and plane waves that are the thing we send onto the atoms. And X here is the quadrature of the electromagnetic field that gets coupled to the atoms themselves. So, of course, this is not something we have invented by far. There's a growing industry of people coupling ultra-cold atoms to cavities in a number of ways. I've here listed some phenomena that have been explored in the last years. Mud insulators have been coupled to cavities. One can exploit dissipation of the cavity to actually produce non-equilibrium states, like time crystals or things that can be characterized as time crystals. There's also a whole physics of spins, like internal degrees of freedom coupled with light, that produces states like squeeze states, which are useful in the context of sensing or metrology. These are just a few examples. I want to mention this review article here, which summarizes the state of the art as it was 4 or 5 years ago. And there you will find also the background discussion on the physical phenomena. In most cases, for what I'm going to present, we can eliminate the photonic degrees of freedom and get only effectively an atomic interaction, and that's now theta square after we've eliminated the photons. So that's actually a proper interaction, density times density. It has a magnitude here, d0, which is controlled by the strength of the interference term between the pump and the cavity laser. And that's something which is directly controlled by, say, the amplitude of the laser beam we send from the side, so we can control the strength and even the sign of this interaction. And then once you do that, this is the theta square here, and that's a Hamiltonian, which if you increase it, if you increase the value of d0 up to very large values, and for example, for positive d0 here, then of course this term is going to dominate, and the system would want to maximize the value of theta, in which case it's going to form the charge density wave that's described here. Right? So how do we observe this experimentally? So we have our atoms here inside the cavity. So we shoot at the atoms from the sides through one of these viewports here. In our experiments, we are at a small angle. And then, of course, if we shoot with a laser that is weak enough, then this d0 parameter here is small, this interaction is small. I told you at the beginning, we are far from atomic resonances, and the system is transparent. So essentially, nothing happens, right? And how will we know that? We just put a single photon counter on the way of the cavity here, and we count how many photons we detect. So 0 here means we see no photons. There's no electric field inside the cavity. But as we increase it above a certain threshold, we start to see a macroscopic population of photons inside the cavity. And where do these photons come from? Well, they are photons from this pump beam that are backscattered by the density wave into the cavity. Because it's exactly what this density wave is actually doing. So from the optics point of view, the refractive index that I had in my cavity has started to acquire a structure which is such that it is now scattering light. So when we see photons here, it means that there is actually ordering inside the cavity. There's a one-to-one correspondence. And I want to mention one thing here is that this is a single run of the experiment. So we are actually recording in real time the system as it evolves under the influence of this external drive. And that's something which is really cool because this is one quantum trajectory. So you really have access to the history of an individual realization as opposed to making averages. And this is, again, not something we are the first to observe. There has been experiments more than 20 years ago by the group of Vlad and Vuletic with laser-cooled atoms. And then a wide range of experiments started with Bose-Einstein condensate in 2010 with the group of Tillman-Esslinger. So we actually produced it for the first time for strongly interacting fermions, in which this long-range interaction that gives rise to this physics is actually large together with the contact interaction that's also large in our system. From the point of view of phase transition, this is a textbook second-order phase transition. It has a Z2 symmetry breaking, so the potential, the free energy landscape looks like this below threshold, and it looks like this above. And what you see here is the electric field amplitude, and you have positive and negative values that are equally likely, and that's the symmetry that gets broken as the transition takes place. Right? The system chooses one side or the other, creates a macroscopic coherent state inside the cavity, which we detect above the transition. And it's really something which, from the point of view of phase transition, is very easy to study. Right? So one thing we've done, you can go below threshold and measure the susceptibility, so the curvature of this free energy landscape. That's something we have been doing here, and we see it shoot up and diverge at the phase transition in ways that are actually very close to what you would expect from simple Landau theory. So the way this order takes place can be actually calculated or estimated using very simple mean field arguments. And the reason why it's supposed to work is, of course, that it's an all-to-all interacting system. So that's a regime in which it's very natural to expect mean field type of physics, well, mean field treatment to be very accurate. We've done a bit more than this. We can also study it in time. So instead of going through the phase transition smoothly, we can just quench above the threshold, in which case we change the free energy landscape from this to that. And then the result of this is that the system is going to start here in an unstable situation and is going to run down here this sort of Mexican hat potential. That's something which can be, I mean, it's a straightforward experiment because we control the laser power in time at basically arbitrarily high speed, if you want. So this is really an instantaneous quench. And then you follow again individual trajectories which now directly track the way the system orders in time. So you can see, for example, an example here in which we've quenched relatively deep in the ordered phase, and we see after some time here, order starting to show up. If you quench closer to the phase transition, it seems it takes a little bit more time, and that's something we can directly trace again. So we have access to the entire dynamics, and that's something which we can study in a little bit more details. If you look carefully at these plots, in particular at the build-up here, you actually realize that this is an exponential rise. So this is now a logarithmic scale for photon numbers. And as far as we can tell, all the way down to our detection floor, this is a pure exponential buildup over more than 2 orders of magnitudes in amplitude. And that's basically, again, the textbook case in which you have an unstable mode which starts to grow exponentially in time. And it seems there's actually nothing else happening, right? And that's, we think, a feature of the long-range character of the interactions. Basically, you have a single mode which grows, and that mode is phase coherent, and it's perfect everywhere, and it appears everywhere at the same time. To some degree, this is a zero-dimensional type of phase transition in which there's no notion of space if everybody is interacting with everybody else. And that's actually something which we can find. So the only thing you need to know basically about the dynamics is the rate at which this is increasing, and that's something we can track now. So this is here on the x-axis, this d0 normalized by the, well, essentially the internal energy of the system. And here you have this growth rate alpha in units of the Fermi energy. As you get close to the phase transition here, the growth is slow, so that is exactly what we expect. There's a diverging time scale involved in the second order phase transitions. And then as we increase the strength and we quench deeper and deeper in the organized phase, the rate at which order grows is actually growing, and it's growing in a sort of completely uninterrupted way. Essentially, well, we were out of laser power at that point, but I'm pretty sure it would still keep going afterwards. And the interesting thing is, which is remarkable, is that this is the Fermi time, if you want, right? So the system can actually order much faster than the Fermi time, which for contact interaction would be completely impossible. Fermi time, it's like a kind of a Joffre-Regel type of limit. Essentially, you cannot go faster than Fermi time if you have contact interaction, because at least you need to have one collision. But here, since an atom interacts with every other atom in the system, no matter how far they are, if they are hundreds of micrometers away from each other, they don't care whether they are bosons or fermions. So in some sense, for long-range interaction, the idea that the Fermi time is an upper bound to how fast the system can order is simply not there. At least this is our interpretation for the fact that the growth rate goes through this without even noticing. And that's even something we can at least semi-quantitatively understand. So that's an analysis that was performed by the groups of Thierry Giamarchi and Eugene Demler for our experiment. You can write down essentially a stability criteria and calculate the growth rate by simply looking at the most unstable mode that you find. And it can be expressed, at least for close to the threshold, as a in terms of the susceptibility of the system. So this is the dynamical susceptibility, the density response function at finite momentum and at finite frequency for the unitary Fermi gas. That's, of course, where it's hard, because now for this object, you need to treat the unitary Fermi gas in the best way you can. So I think here it was done with some RPA type of approach. And that gives rise to the solid line that you see here, which fits relatively nicely. I mean, okay, this is log scale, so this may be a factor of 2 deviation, but at least it tracks relatively nicely over the whole range of parameters that we have explored, the way this growth rate is changing. So alpha is the growth rate. This is an implicit equation that expresses alpha as a function of d0. Right? It's nice, it's actually very robust. So we've done these experiments with non-interacting fermions, with the BEC of molecules, with spin imbalance, with high temperature, everything. All these curves kind of fall on top of each other. Right? And this is, again, a feature which we think is due to the long-range character, that basically all the microscopic details and so on start to go away, and you find something which is effectively has a kind of universal character. So that's another way to study this transition. We've developed a third way after observing it with ramps, quenching, and looking at dynamics. We can actually look at the atoms directly. That's a technology we've developed over the last year. We basically put in the microscope. And I told you at the beginning that since this is the density waves we are producing are at the scales of a micrometer, then you can resolve them with high-resolution optics. It's quite a pain to fit a high-resolution microscope in this machine, but after a lot of effort, we actually managed to see the atoms as they go from the normal to the ordered phase. And these are single pictures below and above threshold, and there you nicely see on individual realizations the very nice stripes. And this is the density wave order that I've been talking about before. That's something we can follow now, both from the photons point of view, but from the atomic point of view as well. There's many things you can do. You can check by Fourier transforming these pictures and looking at the power spectral density that you indeed have this very nice peak. So this is sort of the structure factor, if you want. And you see at the relevant wave vector how order is showing. And it's actually, you can check by checking the width of this pattern here, that this is basically Fourier limited, right? So the width essentially is the inverse size of the system. So order is really there, and it's as clean as it can be throughout the system. And that's something which actually persists. So this is now this peak here as we go from homogeneous to ordered phase. So you see it growing here as you increase the long-range interaction. And if you look at the width, so this is again the inverse correlation length, if you want, it's basically the size of the system all the way down, as far as we can tell, to the self-organization threshold. And that's again a manifestation of the long-range character. There are no defects, no vortices, dislocations of any kind, simply because the system is zero-dimensional. Okay, so this is an overview of how we understand this kind of interaction. Now, the question is, okay, this is, of course, nice. It's well understood to a very large extent. Now, the question is, how can we go beyond that? And let me start with this topic of pair density waves. And for this, we need to go back to how light interacts with the photons. So if you send a photon onto not one atom, but two atoms, now, of course, one thing you can have is that, okay, the photon is absorbed by the first atom or absorbed by the second atom. So that's the boring thing. That's what happens so far in everything I've been telling you. But what you can also have, if the atoms are close enough to each other, is that the photon is absorbed by the two atoms at the same time. And they are absorbed and form a bound state molecule, right? So here, this process is happening. It's a chemical reaction that's triggered by a photon, if you want. Or it's a way to couple two incoming atoms to a molecular state assisted by light. That's another way to say that. It's called photoassociation. That's a very well understood process that has a long history in the field of ultracold gases. But what this means is that if you go away from resonance, so the resonance would be ground to excited transition, and now you start to increase the wavelengths of light, so you decrease the frequency, at some point you will encounter resonances, which are these molecular resonances, by which a single photon is absorbed by pairs and not by individual atoms. And sure enough, if you put this system now in the cavity, from the point of view of photons, these transitions are no different from the other ones. This is just another optical resonance that the medium has, right? So if I look around one of these resonances and I change the wavelength of the cavity, I find a very nice avoided crossing pattern, which is a typical manifestation of strong light-matter coupling in cavity QED, right? So if I didn't tell you that this was a molecular resonance and not an atomic resonance, you wouldn't be able to tell the difference. From the point of view of the atoms, this is, of course, completely different, right? Because now, whether or not this process can take place depends on the fact that there are or not two atoms at the same place, so that there can be these transitions. If there was no pair correlations, or if there was even anti-correlations, that process would not be possible, because I would never have, to begin with, two atoms close to each other. So in contrast with the single photon, single atom interaction, that type of interaction is very sensitive to the fact that the system comprises pairs. And I told you at the beginning, we are working close to a Feshbach resonance at low temperature. We do have nice pairs that are Cooper pairs or strongly coupled pairs. And that's why we have light matter coupling, which is very strong, close to these transitions. So we really have the ability to have photons directly interact with pairs in a way that is independent from the coupling to individual atoms, simply because there happens to be these molecular resonances. And now we can play the same game, right? So if we go away from these resonances here, we are going to work in the dispersive regime of pairs. So there's now two contributions to the index of refraction. One of them is due to the total density of atoms. That's the background effect, if you want. And one of them is due to the total density of pairs. So P dagger P, this is total number of pairs. And there is a coupling here which is independent, which is given by this typical dispersive interaction. Important thing here is that whether I go on one side or on the other, I can change the sign of this coupling here. Right? And that's something you see. So if you think that this effect here is just the refractive index of the atoms changing, what you get, this resonance varying as I change the detuning here is simply saying, okay, the index of refraction of the medium changes, so the effective cavity length is moving. And it's moving one way or the other depending on the sign, and that's because there can be positive or negative contributions to the index of refraction. Okay, so technically, this is the way these pair operator P looks like, so it's really something that kills a fermion in spin up, a fermion in spin down, and there is here some molecular orbital, so it's a short range type of object. The average value of P dagger P is the total number of pairs that I have at short distance. It's a number which is called tense contact. So if you're an expert in cold atoms, that might be something that rings a bell. Or if you followed the lectures of Jean Dalibard a couple of years ago, you will know about this. But this is really where the many-body physics actually is, in the gas, even in the absence of light-matter interaction. And now we do the same thing as I told you at the beginning in this configuration. So we do have the pair density wave coupled to light, and now the charge density wave, and now we have the pair density wave here, which is also coupled with light, with a magnitude here that is something we can actually control. Of course, at the end of the day, the pairs and the pair density wave and the atomic density wave, they are from the same atoms. And the existence of pairs here is related, if you want, by the equation of state. So in somehow, the fact that we have some pairs to couple with here to begin with is because we have contact interactions. So there is a connection between this one and this one, which is directly there. And it's basically telling you that if you change the density, the number of pairs you have is changing accordingly, by an amount which is, a result of the many-body physics that there is in the ground state. So we have these three types of orders that are coupled to each other. And now, of course, the sign here can be changed. So you can have a configuration in which they have all the same sign, in which case they will all contribute in the same way to ordering. So if I look at the photons from the cavity, I will just see more photons, so it's easier for the system to order. But I can also have a situation in which they compete. So I can hinder ordering because of the pair contribution, and that's the thing which we've been studying. So close to this, so that's the same kind of avoided crossing I was showing you before. And now a vertical line on this plot is one of these curves where I was increasing linearly the power of the side laser. At some threshold here, I start to see light in the cavity, and that's a manifestation of the ordering. Now I do this type of experiment for all possible detunings with respect to the molecular transitions, which means I change the strength of this link here, and when I go across, I change the sign. So here we see the threshold bending down, right? And that's the regime in which they all work together. And here we see them actually, this sort of frustration in which the pair contribution is actually going against the density wave ordering. And we actually see here, we see it going high. Here at the threshold, it's a regime where we cannot really work because we have too much losses in the system, but at least the tendencies are relatively clear. This here, this Fano-type profile is what was predicted for our system by the group of Eugene Demler with a relatively simple mean field expression. So to make a long story short, we can keep track now of this, the contribution of these pairs to density wave ordering, and have a regime here in which the strength of the long-range interaction that's necessary to reach ordering is increased or decreased as we go to positive or negative detunings. And that corresponds here to frustration by the presence of pairs or intertwining. That's a fancy language that was brought to us by Eugene to express the fact that they all go together. And we see changes by up to 40% when we go relatively close to the molecular transition. So one can write down, again, a mean field prediction simply by looking again at the stability diagram for the different types of orders. It's a little bit more painful, and it involves not only the density susceptibility, but higher order objects, so density and pair contributions. And these are again objects which for the unitary Fermi gas are relatively complex. I don't think they have been calculated. I think this one has been calculated by Tillman-Hens in some approximations, but these ones I'm not aware of that. So we took different approaches, sort of very simple mean field or equation of states, sort of long wavelength approximations. There are different ways to extract these quantities. These are the solid line and the dashed lines. And as far as, with our limited signal-to-noise ratio, it seems to fit, or at least this tells us that we are on track probably with the qualitative effect we are thinking. But clearly, this is the beginning, and that there are many things which we don't completely understand yet with this kind of system. But at least we now have evidences that we see some genuine pair density contributions, and that's really a different physical phenomenon than just pair density wave plus charge density wave plus background pairing. And that's something which, as far as I know, this is new, and it's probably very different from the type of pair density wave that you might encounter in condensed matter physics, to a degree that I would be actually interested to discuss if some of you have insights. Okay, so let's move now to the last point I wanted to mention, which is, okay, so far we've been discussing situations in which essentially we have density waves, and the reason why we have density waves is because these functions here, they are plane waves, or they are basically inherited from the geometry of the system. If you send a plane wave from the side or a standing wave, if you have a cavity that sustains there's a Fabry-Perot cavity that sustains a cosine mode, then essentially what you are left with is the density wave that exactly matches that. So on the one hand, what we have is really a fermionic quantum systems with long-range all-to-all interaction, but that system has a lot of structure. And what we'd be interested in is making systems that typically looks like this, in which we have, again, all-to-all interactions between a bunch of fermions, but we would like to get rid of this underlying structure that forces the system to adopt this density wave order, which is clearly very different from the physics of the SYK model. Now, there's a very large number of reasons why you would be interested in exploring the SYK model. There has been a whole series of lectures by Antoine about why this model is interesting, what is special and strange, and somehow what's the unexpected thing you want. The motivation for us is relatively simple and actually quite bold if you think about it. That was really brought to us mostly by Julian Sonner, who is a high-energy theoretician at the University of Geneva, and is really pushing us to use quantum simulations to approach models that are relevant for quantum gravities or string theory and this kind of things. Right? And that's, of course, one of them. And the reason why this model is interesting from this point of view is that, at least in the strongly coupled regime, it's a holographic dual of some theory of quantum gravity. So I'm basically no expert whatsoever on that. The holographic correspondence is something which is, it's well established in high energy physics, and it's a mathematically rigorous framework by which, if you think about something you would like to do onto a quantum gravitational system, you can turn this into a prescription of what you would want to do if you had a strongly correlated matter that would fulfill this correspondence. So from my point of view, you can read this as a quantum simulation prescription. It basically tells you, okay, if you're interested in doing experiments with quantum gravity, which, if you think about it, seems a bit mad, it tells you what you would actually want to do on a system which is made of strongly correlated matter without gravity, and what you would need to read out in order to learn the outcome of the measurement you would be doing there. So if you have, so that's why I think it would be really cool to have such a system in the lab, right? Of course, this is kind of difficult. I mean, the number of prescriptions you have to fulfill in order for this correspondence to be valid is actually relatively large, and it's actually unclear whether there exists any physical realization of any system that actually verifies this. I think this is probably still work going on, and the SYK model is the simplest and the best understood model which actually fulfills this, except that, of course, there's no experimental realizations for this. There's a number of proposals. Many of them are summarized in these review articles based on various types of condensed matter devices in relatively extreme configurations. There's even been experiments now in the group of Philip Kim where they try to actually approach this regime, but they are not there yet. We are not there yet either. So, but it will be interesting to see to what extent we can actually get there. So this is where we start from. So now I'm going to tell you the prescription we've devised, the algorithm which we think should bring us to there. And the first thing you need to do is to get rid of these modes, which is perfectly nice interference waves, and introduce disorder into the system. One way we want to do that is we use an atomic physics trick. So the two levels here which give rise to the dipole coupling with light, they are just two levels out of many of the lithium-6 atoms. In particular, we can dress some of the atoms at different places inside our system with light that is resonant between excited states. As a result of this, the energy levels here are going to change from one place to another. And because these levels change, the light-matter coupling is also changing. So basically, we can program a certain function of space, which gives us where we have this blue intensity and where we don't. And that will translate more or less into a laser-defined function here, which is not now a density wave anymore, but which can be actually a random function. Right? So that's the first step. And that's how we get a certain level of programming. By simply designing this function at will and exposing the atoms to it. Of course, you're not there yet, huh? Because now, of course, you have some random function of theta instead of the nice density wave. But sure enough, this system is not SYK. And actually, if you increase D0, you're going to get a macroscopic occupation of theta, and that's nice, but probably not as nice as the SYK physics. And one way to think about it is that you can try to decompose this theta onto atomic orbitals. So say you take a harmonic trap, you have occupations of individual levels of your trap, which you can label with IJKL, do the second quantization, and you will find something in which this density-density interaction will look like that. And there's basically a random amplitude here which reflects the background function you had at the beginning. Right? But it's the same function Jij and JKL, right? So there's just n square coefficients that are random here, but we are not there with SYK because SYK needs n to the 4. But one way to think about it, and the useful way to think about it, is that, okay, Jij times JKL is basically a rank 1 object. If you think of this JIJKL as a big matrix, right? And now, low ranks SYK models have been studied by Ehud Altman, so we know actually how these differ from the SYK model. So basically, you can just count the number of random couplings. So this one is about n to the 4. And one way to think about this is, again, make a rank decomposition of this matrix. So there is a rank R now. And the theorem, or the result, is that to recover the SYK physics, you need the rank of this object to be at least extensive with the number of particles. So there needs to be as many modes as you have particles. And one way to think about it is you need frustration. So you need basically a number of patterns here that are, you need a very large number of these patterns, as large as the atom number, so that the system cannot just fall to a macroscopic occupation of one of them, but it actually has a lot of patterns in which it can organize. Now, the detailed way in which it actually does that is somehow the SYK physics, at least according to these calculations. So what we need to do in our experiment is we just need to go from rank 1 to rank R. And the algorithm to do that, and the thing which we think we can do, is use a sort of trotter approach in which we are going to vary these patterns in time. So you will evolve the system with a certain pattern function f alpha, and then after a short amount of time, you switch to alpha 2, alpha 3, alpha 4, and so on. And if you do it in time, effectively, at the time average level, the Hamiltonian will look like it's the sum of each of these different terms. So basically, every time you add a new independent pattern, you're actually increasing the rank. And if you don't have too many atoms, and if your cavity is good enough, you can accumulate these patterns to the point that R becomes of the order of the number of atoms you have, and the physics of SYK should show up. Right? So in practice, we're going to expose our atoms to random distribution of blue laser intensity, and that has to vary in time. So we know how to do that very quickly, actually. So we've implemented this now in the lab. We've assembled a system that looks like this, that allows us to expose the atoms inside the cavity to essentially computer-defined disorder. Now we can vary this in time in ways that I'm happy to explain later. Technically, it's not completely straightforward. We've shown that this blue dressing trick actually works. So we are able to point at one point in space here and change the coupling locally. And we now do have a bunch of atoms inside this new machine. We are now working with about a few hundreds of atoms, and we are learning how to prepare them in a nice, cold, and reproducible way. So the hope is that in the near future, we're going to try this algorithm, and then we'll see what comes out. Right? So this is what I wanted to tell you. We have this system that combines short-range and long-range interaction, and it's a very nice playground for us to investigate the interplay of pairing and charge density wave ordering in settings where we control all the parameters and where the density wave and the pairing are controlled independently. Right? So it's a very simple instance of competition or intertwining between the two, but that's actually something quite rich, and we can really hopefully learn a bunch of things about this kind of interplay in the future. I show you we can control interactions in time and space, and we hope we're going to get to a point where we can really program this long-range interaction at will, both in a static and in a dynamic way. That's what we are working on right now. And with that at hand, in principle, we can actually do SYK, but we can also do a bunch of programmable interactions in fermionic systems that go beyond SYK, if that's something you're interested in as well. And the last thing I swept under the carpet throughout the entire presentation is, of course, the finite dissipation. The cooperativity we have is finite. And it's fortunate because that's why we can see photons leaking through the cavity mirrors, and we can track how the system evolves in time. That means the system is continuously monitored. And any instance of experiments, being the pair density wave or even potential SYK in the future, will be continuously monitored. And that's something which is very nice for an observable, but it also, in some situations, changes the physics. And that's something which we are starting to learn to what extent this is actually changing the physics. There might be things which are really interesting showing up, like new phenomena originating from dissipation. But it, of course, could be that it ruins some of the plans we have for the future, and that's something we still don't know yet. And with that, I will thank you for your attention and give you here the bunch of references if you're interested in knowing more. And thanks a lot again for the invitation.